Okay, look at this. This is from one of my students from California, and she wrote, please, sir, help me to find the Laplace transform of the function. So we have find the Laplace transform of cos theta u then phi minus pi. Now, it is good to understand that this is an advanced mathematics, especially for engineering and maybe postgraduate students that are pursuing higher advanced mathematics. And this idea of Laplace comes from Pierre Simon Laplace, and it is a common, we commonly call this the Laplace transform. So it is a mathematical operation that converts a function of time. So if you have a function of time, maybe f of t, if I take f of phi, this is a function of time. So this particular operation converts a function of time into maybe a complex variable s. So it will convert this into a complex variable s. Now, how do you handle this that you have? It is generally acceptable in the field of engineering and maybe physics and differential or partial differential equations. So let's look at it and see how you can easily look at this, and maybe you will be able to solve that. If here, this u that you have actually denotes the unit step function, because you can see it is a unit step, and actually it shows you a unit step function. And from what I always tell you guys in class, conceptual understanding. What do you know in terms of Laplace transformation? If I look at a regular cosine function, because this is cosine, so if I take a regular cosine function, let's say I draw it here. So this is a regular cosine function. What you observe in this regular cosine function, what you observe is that if I take a unit function to make it turn on maybe at pi, I will simply have something like this. If I draw a wave that moves in this way, so maybe this is a function of phi, this is t, and if I clean this side up from here to here, then you simply have this. So what you observe from here is that this gives you a pi. That is a pi. This gives you a pi, right? That gives you a pi. So whenever you have a unit in the context of, let's say, Laplace transformation, then we use the second translation theorem. Now, what is the second translation theorem? The second translation theorem states that, if I write that down, second translation theorem, that theorem states that if you have Laplace function, and this Laplace function f of maybe t minus a multiple of u, then t minus a. If you have this function, this must be equal to the exponent of negative a, f of s, where f here represents the frequency and a is nothing but the horizontal translation to be unified. So let me give the cosine a phase shift of pi. So if I give the cosine a phase shift of pi, this is our function, but I want to give that a phase shift of pi. So what you will observe is that we will have the Laplace of this cosine. We are giving it a phase shift of pi, so it will be a cosine of t minus pi. But remember, we add back pi to avoid changing the problem, because the problem says that this is cos t. So for us to add back pi, we will simply do minus pi, then plus pi. Minus pi plus pi. You get that? So if I close this and multiply this by u, and I still have my t minus pi in this side, and close this, then I will now split this apart using the cosine over sum rule. And what is that cosine over sum rule? The cosine of a plus b from basic trigonometry identity states that if you have this function, it simply means we have two functions. Sorry about that. Yeah, so cosine of a plus b is nothing but cosine of a, then cosine of b, minus sine of a, sine of b, sine of b. So this is what you have. So if I try to put what I have in terms of cosine of a, cosine b, what is sine of b? What is sine of b? Sine of b, sine of b, in this case, I can put sine of b to be equals to, because our case in this case we have b is equals to pi, and then we have the whole of cos t minus pi to be equals to a. So the whole of here is our a, right? And pi itself is going to be b. So if this is the case, if that is the case, what this means is that we will plug in our cosine of a. Instead of b, I will put pi. So it is cosine of a plus pi. This gives me cosine of a, then cosine of b, which in this case becomes pi. Right? So it is cosine of pi minus, we'll have sine of a, sine of pi. Again, sine pi is 0. Sine pi is always 0. If I give you sine pi, you can plug that in your calculator. Sine pi is 0. And cosine of pi is negative 1. Cosine of pi is negative 1. So if that is the case, what this means is that we are going to have our cosine. So the whole of cosine of a plus pi is nothing but cosine of a. But then negative 1 multiplied by whole of this will give us negative cosine of a, which prove right, because we know a phase shift of 180 degrees will always negate or give a negative value. If I substitute a back, I will simply have my cosine of phi minus pi plus pi to be equal to negative cosine of t minus pi. Right. So if I put back in the earlier given Laplace equation, I will simply have the Laplace of all this operator, now negative cosine of t minus pi into u, then we have t minus pi. Right. But the negative, we can put it outside the Laplace, such that we have negative outside, then we have Laplace into cosine of now a function exponential negative pi s. Remember, I gave you this as horizontal. Remember, I gave you this formula in terms of the cosine rule, and from a given translation. From a given translation, yes. Okay, that is the second translation. Exponent negative pi s. So this can give you the final. If I rearrange this implies that we have negative s divided by s squared plus 1. Then exponent negative pi s. Hence, this implies that we have negative s exponent negative pi s. Divide this by s squared plus 1. So this becomes the solution of the given Laplace. So this Laplace function that you have here can be written as negative s exponential negative pi s. Divide this by s squared plus 1. So this is how you are able to handle Laplace transformation. I hope I have answered your question. You can watch the previous videos on Laplace for more detailed explanations and how you will solve related questions on Laplace transformation.